I mean, any of those kind of movies, I don't judge them based on like plot holes and crap like that. You know, like I can't stand folks you see online, like after like the latest Transformers movie comes out and they're like talking about some sort of like plot hole in it. Like, look, you just spent an hour and 45 minutes watching robots, alien robots, and explosions. Time well spent. Yeah. That's not the kind of movie you pick apart. But I liked it. I liked Infinity War. I probably liked Infinity War better than Endgame. I don't know. It's tough. Yeah. The first Captain America movie was shockingly good. Yeah. Just kind of that separation between old school and the first superhero thingy, let's say. So I like that one. Winter Soldier, I could take it or leave it. It was fine, but all right. Let's see, where are we at here? We did not have homework for today, right? Okay, we just started. We finished what did we talk about? We had our picture of our languages, right? This guy. All right, so we had all that. We talked about that crap. Talked about how memory used to be super expensive. Then and this is actually after it had already come down in price. Right here, where it says start here. That's where we left off. All right, shut up. All right, so let's talk about the char primitive type here. So we talked about these guys, the byte short, int long last time, and the rationale for why these have different data sizes. And this kind of goes back to memory used to be super expensive. And these guys came from the C programming language, which has been around for a couple of minutes. All right, and they just they've stuck with our modern languages because our modern languages are basically bolt-ons to that older language. So now chars become kind of an interesting thing. So chars are in, we're going to do this for C because I usually do this for Java. So I'll say a char is an 8-bit unsigned integer. And then I'm going to throw in parentheses here, 16-bit unsigned int for Java, C#, and let's just call it newer. So all of our newer languages will represent chars as a 16-bit value instead of an 8-bit value. And I'll talk about why here in a second. All right. So if we kind of expand that out in C, a char can hold, let's see, C, a char can hold values between 0 and 255. We'll just say newer languages. A char can hold values between 0 and 65,535. 65,535. That guy. So 2 to the 8th power, 2 to the 16th power. You don't have to memorize them. It's just a power of 2. So this is 2 to the 8th. This is 2 to the 16th. And the reason why we get to use all of the bits for magnitude is these are unsigned values. They do not hold negative numbers. And we'll talk about why here in a second. All right. So first of all, when we think about our primitive types here, these are the different kinds of values that are built into the programming languages. When we see char kind of sounds like a shorthand for character, right? So when we think about characters, we're thinking about things like an A, a B, a question mark, things like that. single characters in our alphabets, right? But I'm telling you here that a char actually holds numbers, whole numbers, integers, but just only positive ones. So the question is, why? We have these things called character sets. A character set is a mapping between a number and an actual character using some standard. Standards that we're familiar with are ASCII, American Standard Code for Information Interchange, ASCII. So this is an 8-bit, actually it's technically a 7-bit character set. And more recently, Unicode, which is a 16-bit character set. What do you mean lines?
Different parts of it,
like hyphens and yeah, it could do all those things. Yeah.
and darker areas.
No, that's ANSI you're thinking of. Yeah, ANSI is like what are some of the old text-based video games used to get color and stuff. Unrelated.
Okay.
Well, not unrelated in terms of the idea. It is a mapping to a thing.
Gotcha.
It's just not a mapping of a number to a chart.
Gotcha.
All right. So we go, obviously, since C uses ASCII, C++ uses ASCII, and our newer language uses Unicode. Go ahead.
That's supposed to be character, right?
I don't know, maybe.
16 characters.
No, look at this. Hey, I wrote it. This is where it's going to stay.
I just want to make sure
Yeah.
a separate term.
No, yeah, no. It's supposed to be character. It's a new made up term,
Yeah.
and now you're stuck with it for 4 years.
And you better remember.
My jokes last that long. We had a student here, and rest assured, I don't just give nicknames to students just randomly. He kind of got this nickname through his other friends, and it just kind of stuck. But we had this guy here, maybe in 2008, 9, something like that. He was on the football team. His name was Ronique Rose. Really, really ripped, but he was a little short guy, so we decided he wasn't He-Man ripped. He was more like She-Ra ripped. So the football team called him She-Ra. He signed his exam She-Ra, and him and I have stayed friends. He works for the cruise industry. He's worked for a couple different cruise lines, so I visit him down in Florida when my wife and I are down there for cruises and things like that. He still signs all his emails She-Ra. He's in my phone under text messages as She-Ra. So these things are long lasting. If we start a joke that sticks, I'll probably, well, he's bound to outlive me. He's a pretty healthy guy anyways, and a lot younger. But if I were to speak at his funeral, She-Ra would probably be mentioned. All right. In any case, since C and C++ are older languages and they use ASCII, it kind of shows us, this is 7-bit character set versus a 16-bit character set. What does that ultimately mean? It means there's fewer unique characters that can be represented in ASCII than there are that can be represented in Unicode. Okay. Now, how many of you knew that there are more alphabets in this world than just the English alphabet? There's a lot, right? Yeah, there is more. Yeah, according to the C and C++ people, there wasn't. They just had the numbers 0 through 9. Then they had A through Z, upper and lowercase. They had some punctuation stuff. And then they just said, hey, rather than even focus in other languages, we're just going to put smiley faces. They had playing cards as some of the ASCII characters. Yeah, so completely ignorant to the idea that there are other languages. Okay, and this is like in 19, let's call it 1960-ish, something like that. It actually was probably created before that, but let's just call it that. We already knew about other languages. This was just American Standard Code for Information Interchange, kind of closed-minded, let's say. Unicode, Universal Code, has a mentality towards, hey, there are other languages. Now, it doesn't cover every other language that exists on the planet, I'm sure, but it's got a lot of them because there's 65,536 unique characters in the Unicode character set. The first 128 of them mimic the ASCII character set. Okay, so the ASCII character set, their Unicode character set is a superset of ASCII. Which means the first 128 characters in Unicode are identical to ASCII. Which means they didn't have to like go back and change languages and things like that. The ASCII mapping for the letter A is the same as the ASCII or the Unicode mapping for the letter A. Those didn't change. They just added to the end of ASCII more characters and called it Unicode. But in order to do that, they needed to make the number of bits to hold that value bigger. And the reason they went from 8 bits to 16 bits rather than from 8 bits to 12 bits is because 16 is the power of 2. All right. And if they decide, you know, we come out with a bunch of more languages or something, and we need to do whatever the next guy is after Unicode, it'll be a 32-bit language because that's the next power of 2. All right. So at the end of the day, there is like a lookup table that has all of our characters on it, each mapped to a number. So the computer actually stores our characters as numbers. And then when we go to actually use the character, it then does that lookup because computers like numbers better than characters. Human beings like characters. Makes sense? We like to read stuff. We like numbers okay too, but computers represent basically everything as a number. All right. But the idea here is that those character sets, if we are looking through the character set, we say, oh, character 0 is this guy, character 1 is this guy, character 2 is this guy. We don't say character -13 is this guy. It kind of seems incompatible with how human beings think about a lookup table, which is why it is an unsigned value. We don't need to hold negative numbers for this because we're not going to do math with chars, even though we technically could. You could do math with chars because they are technically numbers. All right, questions about chars? All right, floats. Floats and doubles are both they hold numbers with decimal points. So we're moving outside of whole numbers and we're moving to numbers that have decimal points in them, like 3.14, stuff like that. So a float typically is implemented as 16-bit signed before the decimal point. Actually, I'm lying. 32-bit signed before the decimal point and 16-bit unsigned after the decimal point. And this could change based on the language that you're using. But this is a pretty good stab at it. This probably covers the bases of these guys. Where a double is 64 bits signed before the decimal point and 32 bit unsigned after the decimal point. So we can think of floats as kind of like integers and doubles as kind of like longs in terms of the size of the values they can hold. All right. So when you think about a decimal value, we can have positive or negative on the left-hand side, hence the reason that it's 32-bit signed. But after the decimal point, we don't have positive and negative, right? We're going to use that whole thing. You never have positive 3 point negative 24. Yeah, you don't put positives and negative signs after that decimal point in a number. So we don't need to hold a value like that. Yeah.
Wouldn't that be 254?
No.
Okay.
There's 200, 2 to the 8th power is 256
Okay.
unique characters.
Okay.
0 to 255 is 256 unique characters.
Gotcha. Okay.
And this is 65,536 unique characters, which is what 2 to the 16th is.
Gotcha.
All right, so for us, we probably can just think about floats as kind of the decimal point version of integers and doubles as kind of the long version of decimal point numbers. Now, having said all this, and I think I probably said it last class, but I'll reiterate right now, you don't have to go and memorize these numbers. I'm not going to ask you on an exam, what's the range of values that fit inside of a short. I want you to theoretically understand this stuff and see kind of where they came from and why it was built this way. Because remember, our goal here is we're building our modern computer science knowledge on top of a firm foundation. All right. You're never going to be at a job at some point where they're going to ask you some very detailed, how is something represented in bits or something like that. But hopefully we're starting to see patterns that everything's the power of 2. When we looked at the size conversion stuff, we either had a bit was 1, a byte was 8 of those, and then we had 1,024 multipliers up and down. So we can actually represent almost all these things with just a couple of patterns, right? With numbers, we're almost always dealing with powers of 2 in terms of how do computers store this stuff, because that's how computers work. That's how digital logic works. All right. But you don't have to memorize this chart. You'll never have to spit it back out. But I do want you to kind of understand the idea that these aren't just arbitrary values. Okay. A byte is smaller than a short, is smaller than an int, is smaller than a long, and we have multiple ways of holding whole integers, both positive and negative. Rationale being memory used to be really expensive, and that's when these languages were invented. Chars. We want to be able to hold characters. Older languages could hold less unique characters than modern languages, just because we decided that there were more languages that we wanted to be able to represent in the world. So we went from 8 to 16-bit, but it doesn't matter. We could just say modernly, our computers use Unicode character sets, which gives us a bunch of characters from many, 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 many natural languages around the world. Okay, you don't have to memorize that it's 65,536. If you wanted to figure that out, you could just say, oh, it's 2 to the 16th power. But even then, it doesn't matter. You could just think there's a lot, right? A lot of characters. ASCII, not so many, but still plenty, right? Floats and doubles. And here's kind of the interesting thing with this. Last class, we were mentioning that memory used to be really expensive, but now modernly, we don't really think of that as a bottleneck anymore because memory is pretty cheap. So historically, if we were writing code, we truly may have used a short because that might have been the correct tool for the job based on the size value we were going to store. I would say shorts are basically not found in modern programming. If you look at any code that was written anytime recently, nobody's going to define a short in there. Bytes do still exist, but not because of the reason we've explained in here. It's a lot of times with dealing with like video streaming and stuff like that, because the data flows in bite-sized chunks. It's just the right data type for how the data is represented. It has nothing to do with saving space or something like that. Ints are used often, longs are used somewhat often, but usually if you're outgrowing an int, if you need to store a number bigger than 2.1 billion, you're probably jumping over to something object oriented. Like in Java, we have a thing called big integer that can just hold arbitrary size integers, where you just say, look, an int wasn't big enough, so we need to kind of go and get a heavier lifting piece of machinery rather than just bumping to a long. But you'll see longs in the wild these days. So what's interesting is typically a modern programmer, regardless of the size of the whole number they need to hold, will just use an int. So even if they only need to hold the numbers between 1 and 10, where we can look at this and say, oh, well, a byte would have been enough, a modern programmer will just use an int. But we want to understand as computer scientists that that's because we can, not because we should. All right. So we could start the trend of going back and creating variables of, let's be good stewards of our memory and not just waste space and stuff. But, that ship has probably sailed mostly when it comes to that. So if you're storing a whole number and you look at modern programs, very, very, very high percentage that your go-to move is an int. But what's interesting is for floating point numbers, decimal values, you might think that, oh, the default is actually a float. It's not. Our go-to move is typically double for floating point values, just to give us a higher level of precision, something like that. You will see floats somewhat commonly in like game programming, because a lot of times when they're building vectors for like where a pixel is in 3D space, the underlying libraries that they're using, the OpenGL libraries, use floats for those. More just kind of like that argument about bytes. It's the right tool for the job based on how it was built. But it is kind of interesting that we say, we'll just use ints for whole numbers. And we don't just use floats for decimal numbers. We just say, let's go with the big guns and just use doubles. Now, if we go to a language like C, C actually has a couple of other types that we're not showing here. There's a type called a long, which is 128-bit integer type. They also in C allow us to have an unsigned value. So we can specifically say, I want an unsigned int, which then would give us the full precision of the magnitude for an integer and give up the ability to have a negative number. So we would get 0 to 4.2 billion for what an int can hold if we specify that it's going to be unsigned. These are things that you are very, very, very unlikely to ever write yourself unless you were working with something that was based on much older technology. And by then, you're going to have enough computer programming and computer science knowledge maturity that you're going to be able to roll with those punches and say, oh, well, what does unsigned mean? I remember that from my first class. No big deal. Move on with life. I get what it means. All right. So some of these things do exist. I'm mentioning it right now, but I'm not testing you over this. This class is a computer programming class. By the end of the semester, I'm not going to test you over how much crap you can memorize. I want to see what you can do. All right. So once we start getting into the code, which is going to be very soon now, that's where you want to spend your time practicing, not memorizing what's on a slide. If I'm going to ask you to memorize something, like, for example, on the first test, I'm probably going to ask you a question involving that slide about how do human beings solve problems, memory, asking questions, repetition, because it is kind of the starting point for how computer programming is taught. That's the job of our programming languages. And you're going to hear that analogy throughout your education here at Concordia. Even in our language theory class, we talked about that in one of our early slides to remind us the job of a programming language. All right. But so when I go through right before a test, I'll go through the slides and I'll point out the things that, hey, you might want to spend some time on the slide. So nothing's going to be a surprise. I don't throw you a curveball on an exam. That means if you miss something on an exam that I specifically told you in class that will be on there, and I'll do that. I'll specifically tell you, you will have this question on the exam. And then people will still miss it, and then I just laugh. Because it makes no sense. So Other teachers, you might get curveballs or random stuff thrown in an exam. You're not going to get that from me. All right. Lastly, Booleans. These are trues and falses. We use these guys to represent Boolean expressions, which we're going to talk about here pretty soon when we talk about conditionals. Okay, so they're a core part of any programming language. As human beings, we think of these as true or false, like the answer to a question. Okay, it's sunny outside. That's a true statement, right? It's rainy outside. That's a false statement. So in computers, we want to have some way of representing truth. Okay. Now, as you might guess, in our earlier languages like C and C++, Booleans were represented numerically. In fact, even in our modern language, if you dig under the hood enough, they're dealt with numerically. All right. But in C, you can actually do math with Booleans if you wanted to. In fact, in C, we don't even use Booleans. We actually use ints to represent Booleans. C++, they gave us something called a macro called bool that does allow us to say, this is a true or false C thing. And we'll see that by example. Then we get into Java. Java has a type called Boolean. And I promise you under the hood, it's zeros and ones represented as a byte. But from our perspective as the programmer, the primitive values are true and false, and we can't do math with them. Java doesn't let us do math with them. C#, same thing. Swift, same thing. Objective-C uses yeses and nos instead of trues and falses. Just because, I guess. All right, but they ultimately all mean the same thing. All right, so I mentioned this dude changes a little bit depending on the language, because it's not always spelled all the way out like this, but ultimately, true and false used to ask questions. Say that. All right, questions about these primitive types? And once we run out of this stuff, we're not completely lost. This is the kind of values we're allowed to store in our languages. But once we run out of this, our object-oriented languages now provide us some other built-in types that allow us to take this guy to the next step. All right, like I mentioned a few minutes ago, in Java, we have an object type called big integer, which you can literally store an arbitrary size integer in, up until your computer runs out of memory. But as you might imagine, the bigger number you put in there, the slower it gets because of how the numbers work. All right. And when we probably in the next course, the 250 course, we'll actually write our own version of big integer, because, why use something that's built in when you can write it yourself? Yeah, that's a common thing. So I'll actually say it out loud again now. I think maybe I said it in an earlier class. When I give you homework assignments, my intention is for you to solve that program using only what we've introduced in class so far. I promise you, there's almost always a better way of solving it. So I'm asking you to, I'm kind of pretending like you're on a construction site, and I hand you a toolbox and say, this is what you have to work with. Go. Okay. So keep that in mind when you're working on your homework, that Google search that says, oh, I need to reverse a string, and you go and find some library that's built into the language that just magically reverses a string. That's not a good answer, because I didn't give you that library yet for a good reason. I want you to practice the logic under the hood to learn how to do this stuff. All right. So only solve problems using the tools I've given you, even if there is a more convenient way of doing it, which I'll probably show you the next class when we go through the solution. All right. Character sets, blah, blah, blah. All right, I'll just hit this really quick. General purpose languages versus domain specific languages. So as computer programmers, we're pretty much always going to be working with general purpose languages. These are programming languages that are built to solve any kind of problem that a programming language can solve. We go back to this slide right here. All of those are general purpose languages. Okay. In fact, our domain specific languages are almost always written in terms of a general purpose language. So for instance, a lot of times we might call them embedded languages. So like a dishwasher might have a programming language associated with it because it has a little tiny memory chip on there. And, you know, dishwashers only can do like 3, 4, 5 things, you know, like how hard does the water spray? Are we pulling soap from this container? It's not that many magic tricks that a dishwasher can do. So you don't need this full-fledged language. Your dishwasher's not running a video game, right? It's got like 3 or 4 cycles that it knows how to do, and it's just got to do the stuff in the right order with some timers. Make sense? So you might have a domain-specific language for that kind of stuff. All right. So the reality is you're not going to run into domain-specific languages very often, and by the time you do, again, you're going to already be a fairly mature computer programmer, and it's not going to be a big deal. So generally speaking, we're going to be dealing with a general purpose. It can do anything. You can solve problems with a programming language types of languages. All right. So this one is an interesting thing. When we go back to object-oriented versus procedural, when we go back here, and I mentioned last class, these two dudes here. Now, I know I asked in one of our early courses how many people have ever had any programming. We had some hands up. Has anybody in here done programming with an object-oriented language before? Yeah, you want to take a stab at what the difference between object-oriented languages and a procedural language is? How are they different? Besides just a new name that makes it sound, I don't know, cooler or yeah, but I don't want examples of object-oriented. I want what's the difference? Why does a procedural language, why was this guy, let's say, not good enough? Whereas we needed a newer type of language called object-oriented. Yeah.
Did it have like more stuff already predefined?
Okay, there's probably some truth to that, but I would say that has little to do with the fact that it was object-oriented and more to do with the fact that it was just newer, a more modern language. It had more stuff built in. All right, so remind me, what's the job of a programming language? What's a programming language trying to accomplish? Tell a computer what to do, right? And it's acting as an intermediary between us and this dude, right? Hopefully leveraging significantly on our side. You know, we'll give a little. 99% make it human. 1%, well, you know, it's what separates us from the, you know, history majors or the English majors or something like that. I mean, we might not be able to write a paper, but we should know a little bit more about computers than they might, right? Okay, so most of what a programming language is going to do is going to attempt to allow us to solve problems in a way that's similar to how human beings already solve problems. We talked about first, second class, whatever, that the reason why programming is difficult is that we've spent our whole life solving problems in terms of working with other people, human beings, as opposed to telling a computer what to do, where we have to break things down to a lot smaller steps. That's what we're really learning in here is that. All right. So we would say, generically speaking, that the job of a programming language is to provide us a tool that allows us to take our problem-solving abilities and tell a computer what to do. So we want to think about, how do human beings actually solve problems in real life? All right. Now, I talk about this in terms of the procedural telephone versus the object-oriented telephone. So let's say you walked into class today, and over here on this table, I had a giant pile of wires. All right. And I tell you, that's a telephone. And you walk up to it, and you're like, okay, you start fishing through it. You find a handset, you see some buttons, you know, somewhere you pick it up, you hear a dial tone, as if those still exist. So all these things, eventually you're convinced that that is in fact a telephone. But when you first walked in, if I would have said, what is that? You would have said it's a pile of wires. It doesn't look like a telephone, right? When we think about the things in our world, we think about them in terms of the objects that they are. So it's a smartphone, right? We all believe that there's a bunch of complex stuff inside of this dude. But when you just see it, I'm holding an actual object here, right? And the only things that are publicly exposed in this object are a couple like volume buttons on the side, the power button, that kind of stuff. So all the details, we don't actually ever have to go in and mess with an individual wire or an individual circuit or something like that on this thing. All that stuff was built by some smart person, but then hidden inside this object. And only the public interfaces, the things that we actually need to work with to solve problems with this object, are exposed to us. Object-oriented languages give us that. All right. So on this table, we had the procedural telephone, which is the pile of wires that once you fished through all the things that you don't need to interact with to make a phone call, you could get to those parts that you actually need to use to make a phone call. You had to work with a lot of those details, right? Whereas if you came over here and this thing was just sitting on the desk, you could pick it up. Now, do you feel like if I had 3 or 4 different phones sitting on the table, assuming none of them are password protected, do you feel like you could probably accurately make a phone call with anything that is a phone? Yeah, we know enough about the general functionality of a telephone that we could probably make a phone call, right? Regardless of what brand phone it was. All right, because we have a notion in our head about how phone objects work and what we need in terms of the public interfaces at the bare minimum to accomplish the job, accomplish the task for the job it was built to solve. All right, so object-oriented languages are effectively identical to procedural languages with one major difference. I look at it as like a piece of Tupperware. An object-oriented language gives us the ability to create a container called a class and throw that pile of wires into that container, put a lid on it, and poke a couple of holes for the parts of it you actually are going to need to interact with. That's it. That is the only difference between an object-oriented language and a procedural language. It's a level of abstraction to simplify that pile of wires down to the parts that we actually need to use to solve problems. When we're creating our objects, before we put that lid on, we're still going to have to be in there writing the details for all those wires. We still got to write that logic. It doesn't just magically happen for us. But once all the ugly stuff is done, we can slap it inside that box, and now we can pass that box around rather than having to drag this pile of wires with us. That makes sense? Just a level of convenience. So that's the difference between an object-oriented language and a procedural language. It's the ability to create a Tupperware container to hold our extra details. Okay, and it takes us one step closer to being able to solve problems that are similar to the way that human beings can already solve problems before. So we might say, well, why didn't our early languages already do that? Well, when we look back at our very earliest languages, the things that we imagined we would solve, the kinds of problems we imagined we would solve with our computers was very different to what we have today. You know, they were kind of almost toys back then, where we just thought, you know, they were originally existed maybe just in the scientific community, and the fact that you can do math on them was like this, you know, you threw a party, you know, that we got 2 numbers to add together or something like that using some very, very early computer. But as our computers got faster and faster and more memory and more people were using them and trying to imagine, how do we push this to the next level, then the next level, then the next level, we started seeing some weaknesses with those procedural languages. We started trying to solve problems that were complex enough that we said, you know what, Before we had just a couple of wires showing because we weren't implementing an entire telephone in C. Instead, we were implementing something like, I don't know, a toothpick or something like that, something very simple. But as soon as we started using our imagination and started feeling like the computers had enough power that we can start representing more and more complex things, we decided, hey, for a while, I'm just going to make more and more wires, and we're going to see them sitting there, and it makes things seem like, it makes us look so much smarter because we've invented this pile of wires, and oh, you must be amazing in order to work with that. But the reality is we were still only messing around with 2 or 3 of the things of that when we actually used it. When we wrote it, we had to deal with all the details. We believe that some manufacturing place, in this case, it's Samsung, sat there and had to invent this guy. And maybe the initial prototype did have quite a few wires sticking out. But once they finally had final production, they put it on the assembly line and started going through 3D printed or printed circuit boards and stuff. Well, this came off the assembly line. And we know all the details are in here, but we don't have to see them. We don't have to mess with them. And if something goes wrong with this, we don't crack it open and start hitting it with the soldering iron. We take it back to the store and we say, oh, something's wrong. And they say, did you reinstall the software? Yada, yada, yada. And they finally just give you a new one, right? That's how we as human beings solve our typical problems. And as we started demanding of our computers to allow us to solve problems that were more and more complex, we needed that next iteration of our programming languages that gave us the ability to stuff those details in a box. That's what an object-oriented language is. All right, questions about that? All right, I've probably already kind of mentioned something about this. There's no such thing as the best language. What's the right tool for the job for the thing that you're trying to do? All right, if you're doing something in the web world, you're probably going to be leaning towards one of these languages that's kind of designed for webby stuff. If you're over on the native world, if you're writing a Windows application, well, you're probably going to be sitting here working with maybe C# because that's the one that lends itself to Windows applications specifically. If you wanted to work on Windows and Mac and Linux, well, then you're probably going to be looking at Java because that's the path of least resistance to write the program once and have it run on all of them. If you're looking at writing an Android app, well, you're stuck with Java, or there's some cross-platform stuff. If you're looking at writing an iPhone app, you'll be looking at Swift or Objective-C. So all of these are equivalent tools. They're all programming languages. I mentioned the very first day of class, something, or the second day of class, whatever it was, that programming is programming. The language does not matter. Once you understand that 100% of programming languages have facilities for remembering stuff, asking questions, and repetition, if I taught you a brand new language, if you already have a skill set in computer programming, and I say, here's how you remember things in this language, here's how you ask questions in this language, and here's how you do repetition in this language, right then and there, you can already solve a whole bunch of problems using that language, day one. And then you just kind of stumble upon maybe any of the extra features that may have been packaged with that newer language. You know, that make, you know, quality of life stuff that just makes certain things easier, that kind of stuff. All right. So let's look at variables. All right, so we're talking about computer memory. So again, how do human beings solve problems? We remember stuff, we ask questions, and repetition. So we need to have a way, in our case, C and C++. I'm going to use those two terms interchangeably because really C and C++ are the same language until we get to objects. C doesn't support objects, C++ does. All right, so let me jump here. All right, so here's our hello world program. Make that any bigger. And I'm just going to choose C++ as my language here. We'll just stick with that for the semester. So whenever you're working with this, make sure your language you select over here is C++. Here's our Hello World program. We'll talk about some of the details. I think I already looked at some of these details when we looked at Hello World and assembly and that kind of stuff. All right. So we want to start talking about variables here. Syntax for a variable. Go back in here. Call this C/C++ variable syntax. We have the type followed by the name, and then optionally equals the value. So usually optionally would be represented like this. You don't have to give it a value. So I'll show you. So I can say int a is equal to 5, or I can say int a, and then a is equal to 5 on a separate line if I want to. Now C and C++ is case sensitive, so it will care that I have some uppercase and lowercase stuff here, but Keynote updates, fixes stuff instantaneously for me, and I'm not going to spend half the class fixing that. So this allows me to remember something called a, store it, and a is built specifically to hold an integer. And I just happen to be putting a 5 in there. Int a is equal to 5. Printf. Oh, you know what? I think it'll be this will make your life easier. So we're going to use C++ style input output, which lives inside of this thing called the IO stream. So basically, if you just put these 2 lines at the top of all your programs, life will be fine. At some point, we'll talk about that in more detail, but for right now, we want to just give ourselves our platform for saying, I'm practicing some basic programming stuff. So my whole world right now lives between that opening and closing curly brace. Everything outside of that is going to look identical for a little bit. All right, so I'll create an int a, and then I'll say cout a, Endl ends the current line. Oh, I didn't put my semicolon up here. All right, so there's my 5. So I created a bucket of memory named A, built to hold one of those guys, because C and C++ are strongly typed languages. That is, it's a language that requires us to advertise the kind of value that we are going to hold inside of our variable when we first define that variable. Now, you only define a variable once. Once it's defined, I'm going to say you only define a variable once within a single scope. We'll talk about scopes later, because right now, since our entire world lives between these 2 curly braces, we only have one scope. Okay, a scope is where can you access a variable? We only have one, our whole world lives right here right now. Okay, so once we've defined a variable inside of a scope, we no longer have to define it again. We can now use that variable or directly change that variable. So I could say a is equal to 13. And then I can print out a again, and I'll get the 13 the second time. So there's the 5, there's the 13. Notice I only defined a up here where I specified it's built for holding an int, its name is a. Here I'm using something that's already been defined, and I'm changing the value that lives in there to a 13.
What if you put int 1 second?
it'll yell at me saying there's already a variable named A defined. Redeclaration of int A. Only define a variable once. We only, I mean, just like on our actual head, if you already have something stored up here and you know your name, and you try to create another bucket in your head called name, there's going to be collisions and you'll go loopy, right? Right. So only define a variable with the same name once. All right. So variables are how we represent remembering stuff, memory inside of our programming languages. So I'm saying I need a bucket that I want to name A that can hold a number, and the number I want to put in there is a 5.
So you could put a line in there that says A is equal to 5.
Yeah, I can do this. I can say int B, and then I can say B is equal to 2.
Yeah.
Something like that. And this will print out A and B on that line. I'll explain that here in a second. All right, so that's why I said it's optional. I can define a variable, and then later on I can put a value into it. But what you don't want to do is you don't want to define a variable and not put a value into it. And this is actually an interesting thing, depending on which version of their C++ compiler here. In original C and C++, this would not be an error. Even though I technically created a variable called B, but I never put a value in there. Yet I'm trying to print out something that I never set. What we'll probably see here is it probably won't be an error. It'll print out a 0 for B, which typically is the default value for an integer, but you never, ever, 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 ever want to rely on a default value. If you want to create a variable and you expect it to have a value, you put that value in there. All right, so it gave us a 0 for B. If we were looking at a newer language like Java or C#, this would have been an error. It would have said, hey, you are trying to use a variable here that was never initialized. You never gave it a value. So our lesson there is, if you create a variable, always give it a value before you try to use it. Okay? Otherwise, it doesn't make sense. I'm trying to print out the value of B here. What do I expect? I created it, but I didn't put anything in it. But we can define the variable on one line and give it a value someplace else in the program. The only rule would be make sure you give it a value before you try to use it. All right, so let's talk about the cout thing here for a minute. So what we had seen before is printf, which is C's default print function for putting something on the screen. Cout uses what's called an output stream. Doesn't matter how it works under the hood. We're just going to call this the C++ way of doing input output. So it lives inside of a library called IO stream, input output stream. And technically, cout is a function that is found inside of this library called standard. So if I don't say using namespace standard up here, I would have to say std : every single time I wanted to use cout. And since we don't want to do that, we don't want to have extra stuff to make our life harder right now. We want to focus on the programming side of things. I'm just going to say, hey, we're going to be using some crap from the standard namespace. Let's just throw it at the top of all of our programs for now so we have access to that. And then this is how we can write stuff out right here. And the way cout works is it lets us string things together using the double less than sign. So I'm printing out an A followed by a space and space B is : space, followed by whatever B is, followed by this Endl, says end line. It's a built-in thing that effectively is the same thing as that, putting in a \n, which is the escape character for line feed. This will accomplish the exact same output. But typically in C++, Endl ends the line. If I don't put that on there, what'll happen is when it prints out B, it'll be stuck right here at the end of this line, and that 13 will print right after it. It won't have kicked it down the line. So it's visual formatting for us. It's not like every cout has to have Endl at the end of it. It just is, if you want it to print and kick it down a line to print your next crap, put Endl up there so it puts it down on the next line. All right, questions about any of that? Go ahead. I'm not defining it twice. I'm defining it once, and then I'm changing the value of it here. Most recent. So when I print it out here, it's gonna, a variable resolves to its most recent value. A's current value is a 13 here. It used to be a 5 when we were here. All right. Make some sense? Go ahead. Well, I'm choosing not to use printf in here. We certainly can. I'm choosing not to use it since we're going to be using the C++ thing. And now if I want to use printf, I'd have to give ourselves another thing, include standard io.h. It's just another input output library. It's a little bit older. No harm, no foul. Okay, so homework for next class. Write a one-page paper telling me all about Boolean expressions. So look up what a Boolean expression is and tell me all about it. We're going to be using them quite a bit on Tuesday when we look at conditionals, and then we start looking at loops. Questions, comments, concerns, actually, hold on. What have we done? We're not done yet. 250. I thought we were done at 35. We're going to still keep kicking, and this is still going to be your assignment. All right, but we're not done yet. False alarm. All right. So in any case, we're only defining, I'll put some comments in here. So you can do a front slash, and that starts a single line comment. This defines a variable named A. And right here, we're going to say this modifies an already defined variable named A. We can only define a variable once per scope. And when we're defining a variable, you always use the syntax variable type followed by variable name. Optionally, you can give it a value immediately, or you can do what we did here where we gave it a type and a name that now defined an empty bucket that I could then later put a value in if I wanted to. But this line here puts a value in the already defined variable named B. This guy initially defines a variable named B and does not put a starting value in it. Most of the time, most languages, it will get a default value, but in all of our modern languages, it will scream at you if you try to use a variable before you give it a value. Go ahead.
Like, you're just kind of explaining stuff in this call. I'm sorry, just for me personally, I have zero idea what's going on.
Yeah, I'm showing you the examples. All we're doing is introducing the concept of variables, and we're looking at how do you represent variables in C. This is the starting point. Yep. So this is our first jump into code, and I'm saying if I want to remember a number, I can define a memory location to hold a number, and then I can put a number in there. So now I've remembered a number, and I happen to store it inside of a variable called A.
Does that also take into operations, so like 5 plus 10 or?
Yeah, I mean, because all we're doing is using our memory. So if I tell you, remember the number 7, okay, and I say just remember that under something called A. So later on in the class, if I come back and say, oh, what was the value of A again? You would spit out a 7. If I say, go ahead and remember what 7 plus 3 is, or what A plus 3 is, and store that in a B. So now you've created another little storage location in your head called B, and you said, okay, well, A was a 7. You told me to add 3 to it, so now I have a 10 stored in B. So if later on I come back to you and says, what was the value of A again? You'd say, oh, it's 7. What was the value of B? Oh, it's 10, right? That's what we're mimicking here in code. We're creating little storage buckets with names associated with them to remember stuff. Right now, the stuff doesn't have any real meaning, right? We're naming our variables something generic, A and B, and we're just putting arbitrary values in them that we're not necessarily using for anything important. I mean, I could come in here and say int age is equal to 14. So now I've created a variable that seemingly has meaning, that, okay, this is probably someone's age because I named it age, and the value I put in there is 14. So presumably this is the variable about someone whose age is 14. And then I can prove, this is like me coming back to him a few minutes later and say, what was the value of B again? He spits out a 10. So I can prove that age holds that value by printing out the value of age. These don't have to be right next to each other. There can be 10,000 lines of code between these two, as long as it was defined first and had a value was put into it first before I go and try to use it. Okay, but similarly, like he said, I can come down here and I can say, I'm going to change the value of A. A used to be a 5. And now I'm going to say, okay, I want A to actually equal whatever A currently is times 2. Okay, now remember, A started off as 5. It changed to a 13 right here. So when I got here, I'm saying A is going to equal a new value. When A is on the left-hand side of this equal sign, I am assigning a new value to A. What value am I assigning? Whatever the current value of A is. And what's the current value of A? 13. A started off as a 5. It then later on changed to a 13. So by the time I got to this line, A here will resolve to a 13. What's 13 times 2? 26, right? So now I'll go ahead and I'll say cout A. So this is going to print out the current value of A, which has now gone through several iterations, right? But now it should be a 26. So there's my 26 for the current value of A. Go ahead. Yeah, this basically says print stuff.
Okay, and then why is the return 0 necessary?
It's because up here, I've advertised that main returns an int. And I probably mentioned this in class when we were talking about all the assembly stuff, but in older programs, actually in C++, you don't have to have the return 0. But in older programs, a lot of times the only way you would know whether the program worked or didn't work was by the error message you would have gotten out. So sometimes the 0 usually means everything went fine. But you might have a program where something crashes inside of it. So maybe you say, I'm going to return a 4. And a 4 means that the certain thing went wrong. And you might return a 6 other times when that means something else went wrong. So kind of error codes. If you've ever been on a web page where you get like an HTTP request error 500 or something like that, those are, you can go and look up HTTP error code somewhere and see that 400 means this, 500 means this. There's a whole bunch of different things that could have gone wrong in a website. So this is really something left over from programs that would have run in the 70s and 80s where you were running it from the command line, and your only way of knowing whether something bad happened was by the value that's spit out of your program when it was done. Yeah, we're not using it down here. Yeah, so it never gets displayed. Correct. And actually, since we're using C++ here, it should run just fine without it. But C, older C compilers, because of their vintage, they would have assumed that, hey, you're running this program, you really might care whether everything just went okay. So you might ask for the output of that program to see, did what I just do what it was supposed to accomplish? Because not every program is going to output stuff, right? You might have a program that doesn't actually spit anything onto the screen. It might send stuff up to the cloud and store it in a database somewhere. And your only recognition of whether it worked is whether or not the program gave you a reasonable output answer or something. In modern programs, what happens? You know, you fill in a couple of text boxes and hit submit. And if something bad happens, you get a little pop-up window saying something bad happened. It didn't work. So our modern programs have kind of made this idea somewhat antiquated. Not to say that you don't still have programs that are always run from the command line. They still exist. It's just not what we're typically used to, because we're typically, as consumers, used to using graphical user interface operating systems, Windows, Mac OS, whatever. And there's a lot of buttons that we're clicking instead of pressing enter on things and stuff like that. All right, go ahead. Yeah, and we'll see plenty of examples of that. So maybe that'll actually finish the follow through on your question when we write our own functions that spit out an answer, and then we use that answer someplace else. In fact, let me just show you that real quick, just as a, so I'll just create another function up here called add nums, and I'll have this guy take in 2 numbers, and he's just going to return those numbers added together. So then down here, I can say int answer is equal to add nums of A and B. So A currently holds the value 26 we saw. B, what does that one equal? That equals 2. So I'm going to pass 26 in here. I'm going to pass 2 in here. That's going to come up to this function. 26 will pass in here. 2 will pass in here. This will boil down to a 28 that I'm then returning. So this guy right here will boil down to that 28. I'll catch it inside this variable. So I've defined another storage location called answer that's built for holding an integer. And the integer I'm going to put in there is whatever integer is returned by this function call. Okay, so this guy right here ultimately will boil down to that number in this particular case. That's what will end up happening to it. And then I can print out my answer. And see, I have my 28. So that's the nature of that return statement. And we'll see that plenty because we're going to be talking about writing our own functions. So this is just kind of an example, you know, foreshadowing a little bit about where we're going. So we'll talk a lot more about that. I'm not expecting you to know much about that. Today, we're focusing on this world right here where we're defining places to remember stuff, and we're putting stuff in those places, and we're proving what was put in those places by printing it out. That makes sense? And we're doing that in the context of now moving from talking about all that stuff over here in the slides to now actually seeing the C syntax that accomplishes those things. All right, I'll do one more thing here because up to this point, all the variables I created were integers. So now I can create a char, maybe called C, and set this guy equal to the letter A, the character A. So now I can print out the value of the variable C which holds the char A, and this is going to print out to the screen an A. There's my A. So this is another storage container called C, but this guy is built for holding a char. The char I put in there was an A. Go ahead. Single, yeah. So a chars are surrounded by single quotes. Like that. Yep, strings will have the double quotes around it. And what I'll do here, just so you have a starting point, or you can go and review this, I'll go on to Slack channel. I'll go ahead and throw the code that we've been working on here in there, so you can just go through and walk through it and kind of see all those examples. You can go and test it if you want. But the goal today was, now we're seeing C and C++ code, which shows the use of the memory variable things that we've been talking about. All right, questions, comments, concerns, bribes. Remember, homework for Tuesday is this guy. Tell me everything you can find about Boolean expressions, because we're going to use it to talk about conditionals at the beginning of next class. Take care.